Okay, if this one seems a little rushed, it's because I'm having to redo it. Because the first one was too long and wouldn't load. So, did you know that I would like to help and that you should want to help each other also? In other words, I'm getting at the discussion board and how to use it. So, let's go to the discussion board. And first of all, when your MyMathLab opens, it may have a different color, it may not be orange, depends on what section you're in, but when it opens, there should be underneath the course homepage a Piazza discussion board link. It's above syllabus. And if you haven't made any changes, it should look something like what you're seeing here. So I'm going to go ahead and compress the MyMathLab pages so that I just see the panel, what's inside the main panel. And then in a second, I'm going to compress it even further. But this is the Piazza discussion board. Again, if I pan back out, I can see my regular MyMathLab here. So I'm just clicking up here. And I can compress this even further. And if I understand right, like for me, I don't have to sign in each time. Once I've signed in on my computer with Piazza, it remembers me. Maybe you have to do something a little bit different, like check a box somewhere. But every time I log into MyMathLab, it still remembers me in my Piazza account too. That allows me to come in here quickly and answer questions and post things. And there's been students using this, and we were using this to ask a few questions about the midterm and about the syllabus and things like that, about what a probability distribution is. Um, so, and the good thing is some people are asking it, they're figuring out their own problems, but then it causes me to kind of go in there and make a few videos, show you how to use a calculator tutorial and things like that, and then for other people to jump in and answer questions also. So please, please, please use the discussion board. Is it required for the course? No, I didn't want to complicate the grade breakdown, and I didn't really think I had to require this. I figured people would come here and use it if they need it. But I think some of you guys who need it are not using it. So let me demonstrate why you'd want to use it. First of all, it allows me to be more helpful to you because it's a lot easier for me to use the discussion board, and I'm checking this one more often. You may have seen that when I first signed in, it said that there were some items that had not been resolved. Those are things that I just recently did today, so I'm going to go ahead and resolve those since they were my own posts, and then it won't look like I have a bunch of red marks on my account. But let me go to the question. So this is from Jessica. She asked, is there a way to do these sampling distributions on the TI-83? No, not really, not that I know of. Not if I'm understanding your question. So I responded to her that way, and I'm going to demonstrate what I thought she was asking. And if I'm wrong, she'll be able to correct me, and then we can keep the discussion going. But I found an email that I had missed from Tori, who was basically asking the same thing. She was saying, this whole assignment's taking me a long time. Is there some way I can basically use technology to make it go faster? And so let me go ahead and click on the link. And what's nice about her email, as opposed to what we have there in Piazza, is you can ask the question, but it doesn't link you directly to a homework problem, unless you send a homework problem to yourself and then put that link that it sent in the email here. Actually, every time you send me a problem, I think it should send you a problem too. It sends you a copy that you had sent me that question. Anyway, let me find where I put hers. So this was Tori's question. It said the assets in billions of dollars for the four wealthiest people in a particular country are 40, 34, 26, 11. Assume that the samples of size 2 are randomly selected with replacement from this population of only 4 values. They're keeping it small so that they can demonstrate taking all possible samples of size 2 from your population, and then we're going to find out how sampling distributions how they work, but specifically how some sampling distributions will target the population parameter and some won't. And that was in your reading. But I guess we're not going to see all of them, but we'll at least see that the sampling distribution of sample means does equal the population mean. And that's really important because we use that as part of our central limit theorem, part of a result of our central limit theorem. So I've got a sheet already that I set up where I took down the 4 wealthiest people's assets in billions, 40, 34, 26, and 11. And then I just listed this. Now I already did this in a previous video which went foul, and I can't show it to you now. So what I'm demonstrating is this isn't 40 minus 40. I'm just showing you 40, a pick of the number 40, and then a pick of the number 40 again. Now that is what replacement means, or what replacement allows. When you're selecting these with replacement, you're actually doing a simple random sampling instead of just a random sampling. And for a great video on that, if I may point this out right now, go into the multimedia library under chapter 1, chapter 2, I guess. And it is not there, so I'm going to hit all chapters. There's a great animation somewhere in here on how random is random. And if I don't find it here, it might be under here, under sample from a population. Then I'll find it somewhere else and post it. But you had a lot of questions on what the difference was between random and simple random. The difference here is that all possible samples of size n, any n I choose, have the same likely chance of being picked, and every individual item has the same likely chance of being picked. So, and we're making sampling distributions with sample size of 2 right now. So the little dash is a hyphen just saying I've got that sample pair, because 2 is making pairs, right? So I did all the samples that are possible. And now I know that there's 16 possibilities because each time I take a sample, it's a pair, and there are 4 items from my entire population, because it's a really small population, that I can choose from. So that's 2 to the 4th power. In other words, 16 possibilities. And I found the most convenient way for me to organize these is just to say, you know, the first number I'm looking at with itself, and then with the next number, and then with the next number, and then with the next number. So that's the first 4. And then the next number I'm looking at with the first number, and then that's going to cause a repeat when I'm trying to find the means. But then that next number with itself, that next number with the next number, and so on. So you'll see that you're going to have, in terms of the means, you're going to have some cases where the numbers are themselves, you know, paired with themselves, so 11 and 11. Well, that's not bad. I mean, that's how it turns out. But that means that we have, let me scoot this up just a little bit. That means that our first sample, 40 with 40, is going to have a mean of 40. Okay, that's the only time that's going to happen, if all 4 of our original population values are unique. And then we've got 40 with 34, which gives us 37, and then we've got 34 with 40, which gives us 37. So we're actually going to get that twice. So while I've listed the means that go with each of those samples, I'm going to relist them again here. X bar. So for each sample pair, I've got, and I'm gonna list them in order, ascending order, so smallest to largest, and only write 1 for each one. So I'm not going to duplicate it if there's 2 37s. I'm just going to write 37, and then I can write down the probability of those sample means showing up. So let's see here. Pause for a second to do that. Okay, there I have it. Now, as I was doing this, I was also realizing that it's kind of dumb to do it in ascending order when the problem itself had them written in descending order. That doesn't really matter. In fact, I can make that happen right now in a second. So if you look at it, they broke it up into two pieces, but that was just for viewing. You can just imagine you've gone 40, 37, 34, 33, 30, 26, 25.5, 22.5, 18.5, and 11. Just take this second stack on the right and stick it underneath, and imagine it as one stack. So we've got all the probabilities, all of the means, and then we're going to put their corresponding probabilities. So we'll just say P of X bar. And then this will fill in. I said I would go ahead and make this order look the same as theirs, so let me just quickly sort that. It's not hard. From largest to smallest. And what's the probability of having a 40? Well, we can actually look, because our population size was so small that we only got 16 of these. We can just look through the entire list, and we'll see that 40 only shows up once. Well, that makes sense, because that was one of our special cases where 40 was picked, thrown back in, and happened to be picked again, because we were looking at all possibilities of sample size 2. So that's only going to happen 1 out of the entire 16 times. And it wants to make that a date. So let me comment while I'm changing this that everything I'm doing actually can be done on paper. I'm trying to show that you can use Excel for this, but Excel was only handy when I was actually finding out the averages. For everything else, I could have just been doing this on paper. And since they're averages of only 2 items at a time, that really wasn't necessary. Your homework problems aren't going to get too difficult. First of all, we're not going to go much higher than samples of size 2 each, and we're not going to go much bigger than a population of size 4, because that's already at 16 possibilities. Imagine if you were doing samples of size 3 and you were doing a population of size 4. That would be 3 to the 4th power, and that's 81. That would be a lot. Anyway, so what about 37? Well, we know that there were 2 ways that was going to occur, because you could pair 40 and 34, and then 34 and 40, which were unique. And then let me just fill out the rest of these. So what we've got here is a sampling distribution of sample means, and this is a type of probability distribution. We learned about these for the first time in section 5.2. It's been a while, but if you go back to 5.2, you'll remember how we could find the sample mean, how we could find the mean from a sampling distribution. At that point, it wasn't called a sampling distribution, it was just called a probability distribution. In fact, let me go to that page. And the quickest way I can go there is to go into the Dropbox, go to that formula foldout, and this one was described by chapters. So I see here that to find the mean from a probability distribution in general, and a sampling distribution is a type of probability distribution, I would sum up all of the variables times their probabilities. Okay, so what's that mean? That means each time I'm going to take that variable and I'm going to multiply it by its probability. I'm getting something crazy here because it doesn't understand that this is supposed to be a number, so let me convert those back. And let me show you a little bit more detail. Let's see here. Okay, so there's my 1/16, my 2/16, and so on, 1/16, 2/16, 2/16. In fact, remember, to be a probability distribution, there were some requirements, and it doesn't say it here, so let me go to the handouts again and remind us from the statistics review page that the requirements to be a probability distribution is that the sum of all the probabilities had to add up to be 1, and that each of the probabilities needed to be on a range between 0 and 1. Well, that makes sense anyways, because to be a probability, you'd have to be between 0 and 1. So look back here, and when we had them in 16ths, it was probably a little bit easier to read it. I'm going to go ahead and just add them up to make sure that this totals to be 1, and it does. So each of these are probabilities between 0 and 1, and their total is 1. So this makes sense in the section 5.2 thinking framework that this is a probability distribution. Now, I guess that is how we can use the calculator, because the calculator can do all this. If you just put these two lists in, it can do all the summary statistics that I want to do right now. So can StatCrunch, by the way. So let me go ahead and go through this where I multiply each corresponding x times its p of x. So x times p of x, and then I add them all up. So now I need to add them all up. And this value is the expected mean, mu. So this is just the sum of all those values, and then this is mu, the expected mean, 27.75. Now what were we supposed to get out of this problem? We were supposed to get out of this problem that the mean of the sampling distribution of sample means targets the population mean. And that is, we're doing that in section 6.4 because that is the result that we learned about in section 6.5 when we're taught the central limit theorem. Let me go and put in the answers to this homework and see if they ask about that here. Alright, so let's do a quick check. They want these as integers or fractions. Oh, you know what I would assume? That they want the unsimplified fractions. So let me just double check if there was that typo right there. And then I hit clear. Hold on. Let me hit check answer. There you go. And then they say find the mean of the sampling distribution of sample means. And we saw that that was 27.75. And we did that by finding the sum of all the variables times their probabilities. Round to 2 decimals. Well, that's what we had. So there it is. And then, is the mean of the sampling distribution from part B equal to the mean of the sampling distribution of the forward listed values? In other words, does it actually target the population mean? And if so, are those means always equal? Well, that is a big question that you would have to believe from the reading, because we're not actually proving it. Truly, we're not proving it. But that is one of the things that we learned. We learned that the 3 unbiased estimators were the sampling distribution. There was a unbiased estimators for the mean, for the proportions, and for the variances. And then the rest, median, well, all the rest, median, mode, standard deviation, all of those were biased estimators. So they didn't target the population parameter. In this case, the population parameter is mean, mu. Here is the population. We just had 40, we had 34, 26, and 11. If I actually find out the average of those 4 items, I am going to get the same 27.75. This one is called mu, but the real difference is this one is the actual mu. That's that symbol, by the way. If you're not familiar with that symbol, it's called mu. By the way, if you're not familiar with any symbols, that's one of the things that's allowed to be brought to the test. And I may have already ran past it, but here it is, mu. It's the mean of all the values in a population. What we are actually looking at is mu sub x bar, meaning, and I'm going to see if they had that right here. Okay, there it is. mu sub x bar is the mean of the population of all possible sample means. And that depends, well, it doesn't actually depend on n. We chose n as 2 just to demonstrate, but we're saying if you take n to be any size, this is going to be the same thing. And that's a result of the central limit theorem. So maybe I could call this mu sub x bar to be more precise. Anyway, going back to the question to finish it, yes, it does. So yes, the sample mean is equal to the mean of the population. And these means are always equal because the mean is an unbiased estimator. The mean, the variance, and the proportion are all unbiased estimators. So check that answer. Oops. Did I answer what they were asking? Is the mean and sample from part B equal to the mean of the population of the 4 listed one? Yeah, it is. If so, are the means always equal? Yeah, they should always be equal because it's an unbiased. Oh, this says biased. Sorry, 2 letters. Unbiased estimator. Unbiased. They target. You know what? Before I leave, let me look in the PowerPoint. I'll show you a page from the PowerPoint. Okay, so I had to look for a while, but here it is. This is a great demonstration. It's not in your book. They took it out of the 11th edition and out of the 12th edition. But what it was this is an example where they did more than just the sampling distribution of sample means. So they did a smaller population. Instead of a population of 4 items, it's a population of 3 items. And we were behaving as though there were only the numbers 1, 2, and 5. And we looked at all samples of size 2, so similar to ours. Now that's going to be 2 to the 3rd because there's only 3 in the population, where ours was going to be 2 to the 4th. So we had 16, they have 8. But anyway, look at it. Here's the sample, the distribution of means that they had. Okay, and then here's the corresponding probabilities. So if you just take this column here, and that column there, and put them together, you'll get a sampling distribution. Then if you do what we did before, where we, and I'll go to the fold out again, where we added where we summed up all the probabilities, all the variables times their corresponding probabilities, you would have gotten the expected mean. That's mu sub x bar, technically. And that would have been 8/3. Okay? Well, if you would have done that from the original population items, which were just, let me go back up there, got to go higher, which were just the numbers 1, 2, and 5, that's 1 plus 2 is 3 plus 5 is 8. 8 divided by 3, you'd also get 8/3. So you can see that it's actually targeting. Perfect, right? But it doesn't do that for all the calculations. It doesn't work for example, for median. If you did it all for median, you get 8/3 also. And that's because in this case, what is median? Median is the same thing as mean. So these are all going to try to do the same thing as the mean. And then when you do that, you don't get 2, which would be what you're supposed to get for median. Remember, median is you sort the data, and then you take the actual middle number, the middle location, which is the number 2. And that's not the same thing as this 8/3. I mean, even when you round it, 8/3 is 2 and what is it? 2 2/3, which would be rounding to the number 3, not 2. So which ones does it do it for? Well, it doesn't do it for the ranges. The medians are already out. It doesn't do it for the standard deviations, but it does do it for the variances and for the proportions. This was doing a proportions of odds. They could have done proportions of evens. Still would have worked. So it's an unbiased estimator if you're doing the means or the variances or the proportions. So those are the cases in which it's an unbiased estimator. Now, which one matters most to us? The one that matters most is the sampling distribution of sample means, because that's the one that we use for the central limit theorem. And the central limit theorem says that the mean of the sampling distribution of sample means will be exactly the same as the population mean, and that, and of course we're saying n is greater than 30 and so on, and that the standard deviation will be off, but it'll be predictably off. It'll be divided by n, whatever our sample size is. Okay, so I'm going to go ahead and stop the video here and not feel like it's completely answered. I'm going to make a PDF of this little image from the 10th edition of the book for you to kind of mull over and read through to get a better understanding. I'm going to assume that you can always go back through the video, pause, and try to make more sense of it. But to go way back to the beginning of what we were asking, is there a way to do this on the calculator? And the best way you could do it on the calculator would be to actually do exactly what we did on Excel, but as a calculator list. So I'll put it in and I'll show you really fast. Okay, so in list 1, I'm putting all the possible means of samples of size 2, and I'm putting them uniquely and in descending order. So uniquely meaning that, if 237 show up, I'm only writing 37 once. In the next list, I'm listing all the probabilities that correspond to those. Okay, so then I'm going to do like what I did to find the mean and all the summary statistics from a probability distribution in section 5.2 by hitting stat, going over to calculate, choosing one var stats, but doing second one and getting list 1, and then right after that second 2 and getting list 2. So you got to use this comma in between the two of them, and then when you hit enter, it'll find all the single variable statistics. And there's something interesting that happens here. It doesn't show a sample standard deviation because it shouldn't have one. This is the population information, or the expected values. And that's why when you see this little x bar, really what it is it's mu sub x bar. They just don't change the display for it. So here it says mean, but what we mean by mean is we mean mu sub x bar. So 27.75. And part of the thing that indicates to us, first of all, we knew what we were plugging in, but the other thing is, you notice how it said n is 1? Well, there wasn't just one item we plugged in. What that n is 1 is telling you is that they've summed up all the probabilities that correspond, and they turned out to be 1, which is perfect because remember that to be a probability distribution, it has a requirement that the sum of all the probabilities makes 1. Anyhow, obviously I'm saying a lot. It's getting very, very long. I'm going to pause here and still do another video to a follow-up of this one where I show you the things that I told you that were in the help me solve this, the tools for success in the multimedia library. I really want to show you this animation. It bridges all these sampling distribution discussions together into the central limit theorem.